Hello everyone, I'm Dhara Kansara. In this video, I'm going to discuss flip-flop conversions. I will cover the following contents. First, we will see basic important terms related to characteristic table and excitation table. Then we will see truth table, characteristic table and excitation table of different flip-flops. And then we will see flip-flop conversion. In my previous video, I have already discussed the basics, the working of the flip-flop and different types of flip-flops. In this video, we will see how to convert one type of flip-flop to another type of flip-flop. For that, we have to follow these different steps for flip-flop conversion. Okay, there are 5 steps. First step is identify available and required flip-flop. In the question, 2 flip-flops are given. We have to find out what is the available flip-flop and what is the required flip-flop. We have to convert one type to another. That's why we'll find available and required flip-flop. Second step is make characteristic table for required flip-flop. Third step, make excitation table for available flip-flop and also create excitation table for step 2 table. Then in step 4, we have to write Boolean expression for available flip-flop from the K-map. In the step 5, we'll draw the logic circuit diagram from the given Boolean expression. Okay, so now going to main point, we will discuss what is the characteristic table and what is the excitation table. So characteristic table defines the present state of flip-flop in terms of flip-flop input and previous state. Means here in the characteristic table, inputs are the input of the flip-flop and previous state. And the output is present state. Don't worry, we will see in detail in some time. Now, excitation table. Excitation table is needed to know what will be output of system, as in it tells us for what set of input we will get what output. So here inputs are present state as well as previous state and outputs are flip-flop inputs. Okay, fine. Okay, now we will see truth table, characteristic table and excitation table of different types of flip-flops. This is what truth table of SR flip-flop. As we have already discussed in my previous video, this truth table of the SR flip-flop. Here in this table, we are using clock signal. These are the inputs and this is the output. Now suppose S means set, R means reset. Now suppose both the inputs are 0, we will get Qn plus 1 is equal to Qn. Qn plus 1 is present state and Qn is previous state. Means both inputs are, if both inputs are 0, then there is no change in the state. That's why I have written NC. There is no change in the state. Now suppose if S is 0, R is 1, then flip-flop will be goes in reset mode. That's why Qn plus 1 present state is equal to 0. Flip-flop will be reset. If S is 1, R is 0, then present state will be 1. Means flip-flop goes in set mode. If both inputs are 1, then present state will be invalid. This state we cannot use practically. Now come to this table, characteristic table. To write this characteristic table, we will use this truth table for our reference. Here you can see in this truth table, to define this present state, we are using previous state, Qn. So in this characteristic table, we will use Qn as an input, because to define this Qn plus 1, we are using previous state, that is Qn. And both the inputs, that are S and R. So 3 inputs are there in characteristic table Qn, S, R. This is what Qn plus 1 is the present state. Okay. Now, we will refer this table for these different combinations. Here you can see 3 inputs are there, so number of possible combinations will be 8. Now suppose S is 0, R is 0, S is 0, R is 0. At that time Qn plus 1 is what? Qn, means there is no change in the state. So here 0, 0 means there is no change in the state, means previous state. Previous state is Qn and the value of Qn is here 0. So here we will write simply 0. Why? Because there is no change in the state. So 0 we are getting as previous at present state. Okay. Now suppose S is 0, R is 1. You can see here S is 0, R is 1. We are getting 0. Okay. So we'll write here 0. If S is 1, R is 0. If S is 1, R is 0. Qn plus 1 is what? 1. So that's why we have written here 1. Okay. If S is 1, R is 1, then invalid state means neither 1 nor 0. That's why we'll write don't care condition for that. Okay. Don't care means simply you have to write cross. Now, if S and R, again, suppose both are 0 and previous state is 1, then as I told you, there is no change in the state. There is no change in the present state. So we will write here 1 as it is. When 0, 1, Qn plus 1 is 0, 1, 0, Qn plus 1 is 1, 1, 1, invalid state. So like this way, we can write characteristic table. Now we'll see excitation table. So in the excitation table, as I told you, inputs are what? Qn and Qn plus 1, previous state and present state. And this is what? Inputs S and R. Okay, now to design this excitation table, we will refer characteristic table. You can see here, I am using Qn and Qn plus 1, 2 inputs. So 2 inputs are there, 4 possible combinations are there, 0, 0, 0, 1, 1, 0, 1, 1. Now I will refer this characteristic table to fill this data. If suppose Qn and Qn plus 1 both are 0, I will refer this table now. Qn is 0, Qn plus 1 is 0. Another possibility is there, yes, this is what? Qn is 0 and Qn plus 1 is 0. The same combination we are getting here also. Qn is 0, Qn plus 1 is 0. At that time, S is not changing from this state to this state. Whenever I am moving from this state to this state, this S is not changing. S is stable, 0. But R is changing from 0 to 1. So whenever both the states Qn and Qn plus 1 are 0, we'll write S is 0, but R is cross, means either 0 or 1. Here you can see whenever Qn and Qn plus 1 both are 0, we'll write 0x. Okay, when Qn is 0, Qn plus 1 is 1. Qn is 0. Qn plus 1 is 1. This is only one possibility here. So for that, S is 1, R is 0. S is 1, R is 0. Qn, if Qn is 1, Qn plus 1 is 0. If Qn is 1 and Qn plus 1 is 0. For that, S is 0, R is 1. S is 0, R is 1. When both the states Qn and Qn plus 1 are 1, 1. So now here you can see Qn is 1 here for this combination. Qn is 1, Qn plus is 1, S are 0. Both are 0. There is another possibility. Here you can see same combinations we are getting here. So this is what Qn is 1, Qn plus is 1, but at that time S is changing from 0 to 1, but R is stable. That's why we will write S is equal to cross, means S we will consider it as don't care condition. R is 0, so that's why we'll write X 0. Fine. Now for the JK flip-flop. Similarly, first we will write truth table. From the truth table, we will write the characteristic table. From the characteristic table, we can design excitation table. Now in the JK flip-flop, these three outputs will be same. Means for this three combinations 0 0 0 1 1 0, output will be same as we have seen in the SR flip-flop, but the change in the last combination, that is Qn bar, means whenever J and K both are 1, this Qn plus 1 present state will be complement of previous state. Suppose Qn bar is 0, previous state is 0, then here we will get 1. If previous state is 1, then here we will get 0 whenever both the inputs are 1. So this is what truth table. Now characteristic table. From this, we have to define the characteristic table. As I told you, we will use here, these three are the input, previous state, J and K. These three are the inputs, and Qn plus 1 is the present state. Okay, so these are the three inputs. So possible combinations will be A. Now suppose to write this table, we will refer this truth table. Now suppose J and K both are 0. You can see here J and K both are 0. Then there is no change in the state, present state. There is no change in the present state. So Qn, this is what previous state. We are getting 0 as it is in the present state. Whenever J is 0, K is 1, J is 0, K is 1, Qn plus 1 is 0. Like this way, you can complete the table by using this truth table. Now we'll design excitation table. Here, you can see these two are the inputs. I mean, previous state and present states are the input and outputs are J and K. Means for this combinations, what should be the input? Okay. Now suppose both Qn and Qn plus 1 are 0. You can refer this characteristic table. Both Qn and Qn plus 1 are 0. At that time, J is not changing, but K is changing from 0 to 1. So in this excitation table, we will write J is 0, but K as don't care. Means neither 0 nor 1. That's why we'll write here cross, don't care condition. Similarly, for another combinations, you can fill this table. So this is what three tables for JK flip-flop. Now these three tables given for the D flip-flop and T flip-flop also. The steps will be same. First you have to write the truth table. From the truth table you can design characteristic table, and from the characteristic table you can write excitation table. But now we will see flip-flop conversion. Okay, suppose we'll solve one example. Suppose I want to convert JK flip-flop to D flip-flop. So in the first step, what we'll do, identify available and required flip-flop. Here available flip-flop is JK. Why? Because we want to convert JK to D. So available is JK, but we want D flip-flop. That's why required flip-flop is D. Second step, characteristic table for required flip-flop. Here required flip-flop is D. So we'll write characteristic table for D flip-flop. That is given, that is already given here. Okay, characteristic table of D flip-flop. Fine. Now in the third step, write excitation table for available flip-flop. Available is JK. So for that we will write excitation table. And similarly, in step 3 only, we have to create excitation table for step 2 table. For this table, we have to write excitation table. So these are the step 3, these two tables comes in step 3 only. Okay. So in this step, what we'll do, this is slightly different. You can see here what I have written, create excitation table for step 2 table. Means for this table, we have to write the excitation table. That is known as conversion table. Now, suppose what we'll do here, we will write this table as it is. As it is, I have taken this table here. Now, this is what output J and K of this step number 3. Okay. Now what we'll do for these combinations, say Qn is 0, Qn plus 1 is 0, we will refer this table only. We will write the value of J and K from here. So at that time, J is 0 and K is X. Now suppose Qn is 0 and Qn plus 1 is 1. Qn is 0 and Qn plus 1 is 1. At that time, J is 1 and K is cross. I mean, don't care. Okay, like this way you can complete this table. This is what? Conversion table. In step 4, what we have to do? We have to draw the K-map for these outputs, J and K. So we will draw K-map separately for J and K. Here you can see K-map for J, and this is what K-map for K output. But you have to remember that you have to consider these 2 inputs only. Don't consider this Qn plus 1. Here you can see D and Qn. We are not considering Qn plus 1 here. Means present state we are not considering in this K-map. Okay, so J is 1 for this combination. Qn is 0 and D is 1. And J is don't care for this combination. So we'll put this value here in this K-map and we'll write, we'll make a pair and we'll write the equation. So here we are getting J is equal to D and K is equal to D bar. We have already discussed how to write and how to draw this K-map and how to write this logic equation. In our previous video, we have already discussed. So this is what J is equal to D, K is equal to D bar. So now we can draw the circuit. In step number 5, we can draw the circuit. For that, what we'll do, we will draw the symbol of the given flip-flop. Means here JK is given, JK flip-flop is given. So we'll draw the symbol of JK flip-flop. Here JK are the inputs, clock is input, and these are the outputs. Now what is J? J is nothing but D. So we'll apply D to directly J input. What is K? K is D bar. So simply we are using this inverter. We'll convert this D to D bar. So here we are getting D bar. This D bar we are applying to K input. Okay. So this is what? Conversion of flip-flop. Conversion of JK flip-flop to D flip-flop. This circuit follow the D flip-flop function. Okay. Now we will see the second example. Convert SR flip-flop into JK flip-flop. So the steps are same. You have to follow the same steps as we have discussed in the previous example. Okay, so this is what conversion table. Here, convert SR flip-flop into JK means available flip-flop is SR and required flip-flop is JK. So SR is you have to write here and JK you have to write here. Means JK are the inputs and these are the outputs. Okay, so this is what conversion table. From the conversion table, you have to draw the K-map, and from the K-map, you have to write the logic equation. From this logic equation, you can draw the circuit. Now, available flip-flop is SR, so we will draw the symbol for SR flip-flop. Then, what is S? S is nothing but J, Q, P bar. Okay, so this is what AND gate operation. So in this AND gate, we are applying J as well as QP bar. Okay, so this QP bar, this complemented output, we are applying to this one input, and the second input we are applying J. Okay, so these 2 inputs, J and QP bar, here we are applying to S input. Now what is R? R is nothing but K into QP. So simply we will give two inputs to this AND gate. That is, one is K and simple. The second input is QP bar. So we will give this QP bar here. And output of this logic AND gate we are applying to R. Okay, students. Thank you.